So the last bonding theory that we're going to talk about is called molecular orbital theory. And in this theory, we're looking at calculating the orbitals for the entire molecule instead of for individual atoms. So Lewis theory and just basic quantum mechanics, we're looking at these atomic orbitals, and when things bonded, atoms bonded to other atoms, those orbitals didn't change, they stayed the same. And that's a very simplified view. In valence bond theory, we looked at the hybridization of atomic orbitals. So on a given atom, its orbitals would hybridize and change to better bond with other atoms. But those orbitals were still localized on that single atom. In this model, now, we're taking the orbitals from all the atoms in the molecule, basically, and hybridizing them together. So this is much more encompassing. It's also more difficult. Okay, so to solve the Schrodinger equation, even for a simple diatomic molecule, is actually impossible. So they use a trial function as an educated guess and see how that works. And then they, basically it's iteration, you change it a little bit and see if that makes it better. And so computers are going to calculate the energy for the trial functions, and then they optimize it for the lowest energy. And so that's our approximating what nature is doing. We'll never do as well as nature does at approximating that. So this is way beyond the scope of this class to understand all of that. So what I'm going to try to teach you is enough so that if you take organic chemistry, you will know what they're talking about, okay? You'll be like, oh yeah, I've heard of that. I'm okay with that, okay? So I am not going to require lots and lots of detail from you on this, but I want you to, try to stick with me here. So here we're talking about LCAO, a linear combination of atomic orbitals. And so here we've got basically a weighted linear sum, which is basically an average of the valence atomic orbitals of all the atoms in the molecule. And just a reminder there, valence bond theory hybridizes orbitals only on a single atom, and here basically we're hybridizing them on all the atoms. So these linear combination of atomic orbitals are going to be delocalized over the entire molecule, whereas the hybrid orbitals are localized on a single atom. So we are going to look at very simple diatomic molecules, meaning two atoms. And we're going to start with two atoms of the same element. So you can't get much simpler than H2, right? So H2, so we have one hydrogen here. It only has one electron, that is the valence electron. It's in the 1s orbital. And the other hydrogen also has an electron in the 1s orbital. So we're doing this linear combination of those two orbitals. So we can combine those in a way that they reinforce each other, adding them together, and we get this sort of a shape. So you have to use your imagination a little bit. This is lower in energy than the original orbitals. It's called a bonding orbital because when the electrons are in here, the energy is lowered, and that promotes the formation of the bond. This is called a sigma orbital. So sigma and pi will be used in this theory as well. Remember, in valence bond theory, a sigma bond, right, was cylindrical, right? It was spherical from the end, symmetrical, kind of shaped like the sigma. So if you imagine looking at this from the end, it's like a sausage or a hot dog or something, right? It's round. So this is a bonding orbital. The next one is made by combining an s orbital in a positive phase with an s orbital in a negative phase. So waves have phases. They can be above the axis or below, right? And so we're not used to looking at s orbitals as having phases because when you draw them, you can only see one at a time, but they can be either. So in essence, this is like subtracting. So instead of constructive interference, this is destructive interference. So just like those waves that ran into each other, the ripples in the lake, they canceled each other out, right? So here, these are canceling each other out right there in the middle. So there's a node in the middle where the electrons cannot be. This is called an antibonding orbital. It's higher in energy than the original orbitals. So if we have electrons in this orbital, it raises the energy of the molecule, and that does not promote the stability of the molecule. It works against bonding, anti-bonding. So this is called sigma star 1s. This previous one was sigma 1s because it's a sigma orbital formed from 1s orbitals. And here, sigma star, that means it's the antibonding orbital. It's higher in energy. Any questions yet? Yeah.
So whenever there's a star, it's the antibonding?
Mm-hmm. The star indicates antibonding. The antibonding is always going to be higher in energy than the bonding. So if you combine two orbitals, you still have to end up with two orbitals, right? So we're going to get one that's lower in energy and one that's higher in energy. So if we have these two orbitals being added together to get destructive interference, essentially subtracting, then we get this antibonding orbital, which is higher in energy. If we have constructive interference, these orbitals reinforce each other, and this is lower in energy. It's a bonding orbital. So here we have high electron density between the nuclei, which makes sense. It promotes bonding, holding those two nuclei together. Here we have a region of 0 electron density between the two atoms. So we make diagrams, we made orbital diagrams for atomic orbitals before. And so these are sort of related to those. So here we have the orbital diagram for one hydrogen atom, right? The 1s orbital, we've got a box here, and we have an arrow pointing up. That's one electron there. Here we have the other hydrogen atom. It also has a 1s orbital. Here's its box. Here we've made the arrow pointing down because we know that we're going to combine these two, and the only way that two electrons can be in an orbital together is to spin pair. One has to be up, one has to be down. So we don't normally draw them like this just on their own, but that's why it's drawn upside down. So when these two atomic orbitals are combined, we get one bonding orbital, which is lower in energy, and one antibonding orbital, which is higher in energy. Okay? You just, a lot of this is like, well, okay, if you say so, right? I'm not expecting much understanding here. Honestly, I don't have a real great understanding of it myself. I know what I need to know, right? So that's what I'm trying to teach you, is just as much as you need to know. So these are the molecular orbitals then. This is a sigma 1s and sigma star 1s. So when we put electrons into the molecular orbital diagram, we're going to follow the same rules we've used for other ones, right? The first electron goes in right side up. Think of the hotel bed. The first person is going to sleep right side up because of course you would. If another person comes and sleeps, you can't sleep on the floor because the floor is lava, so they're going to sleep upside down, right? You're going to take the cheapest room, the lowest energy orbital first, before you start filling up more expensive ones. So in this modified hotel, we've got two rooms here. This one's cheaper, and that one's more expensive. We've got two electrons coming in. The first electron's going to sleep right side up here, and the second one's going to go upside down. They're going to avoid that room because it costs too much energy, too much money. Okay? Now, we talk about something called bond order. And really, this is just comparing, okay, how many electrons are in orbitals that promote bonding versus ones that don't promote bonding. So it's the bonding electrons minus the anti-bonding electrons divided by 2. So it's kind of an average. So let's go back and look at that diagram again. So we're looking at the molecular orbitals, and we're going to take the number of electrons that are in bonding orbitals. So this is the bonding orbital, 2 electrons. And we're going to subtract the ones in anti-bonding orbitals, because those are fighting against making a bond. Okay? So these are promoting the bond. If there's any up there, they're fighting against the bond. So here I've got 2 minus 0, and then we're going to divide it by 2 because we're looking at 2 different atoms like an average. We're dividing by 2. So for hydrogen, we get a bond order of 1. A positive bond order predicts that that chemical bond will form because it tells us overall the electrons are going to have lower energy. The larger the positive number here, the stronger the bond. It tells us there are even more bonding electrons than anti-bonding. If that bond order is 0 or even negative, then a bond will not form. You could end up with a negative bond order if you had more anti-bonding electrons than bonding electrons. So let's look at the next most simple molecule, He2. So here we have a helium atom. It's got 2 electrons. This is its orbital diagram. Here's the other helium atom. Again, we're combining 2 1s orbitals, and so we get 2 new orbitals. One is lower in energy, sigma 1s. One is higher in energy, sigma star 1s. That always happens when you have 2 s orbitals combining. You get one that's lower and one that's higher. And then to fill this in, we're just going to look at how many electrons do we have. Well, I have 2 from this helium and 2 from that helium. So how do we put them in? Same way we filled orbital diagrams before. You put them in one right side up here, then upside down. Now that cheap room is full, they have to go to the more expensive, the higher energy. So again, first one's right side up, second one's upside down. We've used up all of our electrons, we're done. Okay? And then we need to know how to look at the bond order for this. So the bond order is the number of electrons in the bonding orbitals. There's 2 in the bonding orbitals, minus the number in the anti-bonding orbitals, the ones with the asterisks. So I've got 2 minus 2, and then I'm going to divide that by 2 because I'm averaging, and so I get a bond order of 0. What does that predict about this molecule? Is this going to be a stable bond between 2 helium atoms? No. So molecular orbital theory here predicts that the He2 molecule is not stable. And what have we learned about the noble gases? They don't bond with each other, right? They barely bond with anything, and helium doesn't bond with anything at all. Because helium's just like so smug and self-centered and just all fine in its own business, right? So there we go. He2 should not exist. Well, what if we're missing an electron? And we have a helium atom and a helium plus ion. We've not talked about those at all, but how would you make an He plus ion? You take your helium atom and you take one of the electrons away. Is it going to like that? No, it's not, but we don't have to worry about that. So again, we've just got these same 1s and 1s. They combine. We get a bonding lower in energy and an anti-bonding higher in energy. The difference here is now we only have 3 electrons to place instead of 4. So the first one goes down here, and the second one goes down there, and the third one goes up here. Okay? Then we calculate the bond order. It's the number of bonding orbitals, number of electrons in bonding orbitals. So there's 2. Minus how many in the antibonding? There's 1 there, right? And then we're going to divide that by 2. So 2 minus 1 is 1, divided by 2, so we get 1/2. So that's a positive bond order. It's really small, but it is a positive bond order. So that predicts that the He2 plus ion exists. And it does. Well, it's not very common, but it can exist. So this is like a summary slide. So we're approximating those molecular orbitals, which are really, really complicated to actually calculate, by just looking at basically an average of the atomic orbitals. The number of molecular orbitals has to equal the number of atomic orbitals. So you could say, the number of orbitals is conserved. In the hotel analogy, you've got a certain number of beds, right? And no matter how you move walls around, you still have the same number of beds, okay? When we combine 2 atomic orbitals, so you'll form 2 molecular orbitals. One's lower in energy, the bonding, one's higher, antibonding. When we put electrons in there, we're going to follow the same rules. We're going to fill the low energy ones first with up to 2 spin paired. So you can't have 2 right side up. They have to be opposite in spin. And then we'll also follow Hund's rule, which is if there's an empty bed, you're going to take your own bed instead of sharing with a stranger, right? From the hotel analogy. That's Hund's rule. And the other idea here is that to have a stable bond, you have to have a positive bond order, which really just says you have more bonding electrons than antibonding electrons. Okay. Use molecular orbital theory to predict the bond order in H2+. Is that bond stronger or weaker than the H2 bond? So, if you remember, the bond order for H2 was 1. So that's what we're going to be comparing it to. So here I've got the 1s orbital for 1 hydrogen. And here I've got a 1s orbital for the other hydrogen. And so when these combine, I'm going to get 1 orbital that's lower in energy. I didn't plan this out very well with the grid. And 1 that's higher. And so this is called sigma 1s, and this is sigma star 1s. So these are the atomic orbitals on the sides, and these are the molecular orbitals in the middle. So here I've got H2 plus. So that must be the combination of a hydrogen atom and a hydrogen ion, right? So my hydrogen atom has 1 electron. It's going to be sitting there in the 1s orbital. How many electrons does an H plus ion have? None. So that box is blank. So now we're going to fill in our molecular orbitals. How many electrons do we have? There's only 1. So it's got to go down here, right? It's going to go in the lowest orbital, lowest energy orbital. And then we're done filling in the electrons because there was only the 1 electron. We're starting small here. What's the bond order? How many bonding electrons are there? 1, just that one, right? This is a bonding orbital. And how many in the antibonding orbital? 0. And then It's an average, so we're dividing by 2. So this is going to give me a bond order for this thing of 1/2. So is this bond stronger or weaker than the bond for H2? It's weaker because it is a smaller positive number. This predicts that this ion does form, but the H2 molecule is more stable. Any questions? So we're going to be looking here at homonuclear diatomic molecules. So homo is a prefix that means the same. Homonuclear, same nucleus. So these are atoms of the same element. Diatomic, 2 atoms. So all of these that we're going to look at now, there are 2 atoms of the same element. So this is Li2. It's a lithium atom and another lithium atom. So we're getting into period 2. Now we did period 1, hydrogen and helium. Period 2, we've got lithium. And we're just going to look at the valence electrons here. So we have 1 electron in the 2s orbital for lithium, and this one also has 1 electron in the 2s orbital. That's the orbital diagram that we know and love, or maybe that we're okay with. The 2s orbitals are going to combine just like the 1s orbitals did to form one that's lower in energy and one that's higher. Bonding and antibonding. And then we're going to take these 2 valence electrons and we're going to put them into our molecular orbitals. And so they're both going to go in here in the bonding orbital because that's the lowest energy. And so calculating the bond order, number of bonding electrons is 2. Subtract the number in antibonding orbitals, which is 0. That quantity divided by 2, and so this has a bond order of 1. Li2 does exist in the gas phase. It's not a common thing. You're like, well, I thought lithium was a metal, and how are we forming a molecule with metals? Okay, you remember I said we lied to you about some things, right? Just to make things a little simpler. So this is where we just don't want to think about it too hard, okay? Next element, beryllium. So beryllium also has the 2s orbital as its only valence orbital. It's got 2 electrons in there. Here's the other 2s orbital. We combine those, we're getting the same thing we've gotten for everything else. One that's lower in energy, one that's higher. I've got 2 electrons here, 2 electrons there, total of 4. I fill them in. It goes 1, 2, 3, 4. And then bond order. How many electrons in bonding orbitals? Well, there's 2. How many in the antibonding orbital? Also 2. Divided by 2, and so that's a bond order of 0. So this one is predicted to not exist or to be unstable, and that is true. When we get to boron, now we have to include the p orbitals, the p atomic orbitals. So each atom has 3 p orbitals, right? And they're arranged perpendicular to each other. So we're going to look first at the ones along the x-axis, and we're saying that that's the line connecting the 2 nuclei. So when we look at a p orbital, one side has a positive phase and one lobe has a negative phase, because this is like a standing wave, and this part's negative and that part's positive. So here we can look at, well, how are these going to combine? If I put these together so that the blue parts overlap, they're going to reinforce each other, and they're going to make this bonding orbital. So the blue part gets big and bulgy and merges into one thing, and that kind of makes sense. This is putting them together with the opposite. So I'm going to flip this one around. So I'm going to take them like this and overlap them. And so here I have a positive wave and a negative wave, and those are going to cancel each other out. And so I'm going to get a node in here. And then over here I've got that blue one, and on here I've got the red one. So this is going to be higher in energy, an anti-bonding orbital. These are also sigma orbitals, because just like the sigma bonds in valence bond theory, it's the end-to-end overlap of the p orbitals. So this is sigma 2p, because it's formed from the 2p orbitals, and this is sigma star 2p. Any questions? What about the others? So we have another pair of orbitals that are in the y-axis, okay? So those can overlap in a positive or a negative way as well. So here they're shown with their phases matching, right? So we've got the blue in the back and the red in the front. So when these combine together, we're going to get one big bulgy thing in the back that has a positive phase, and one big bulgy thing in the front that has a negative phase. It's reinforcement. The wave got bigger, right? When the crests of the wave interfere with the crests of the wave. And then here is flipping this one and adding it backwards, or you can think of subtracting. But here we've got blue interacting with red, and they're going to cancel each other out. And so again, we're going to get this node in the middle where there's no electron density. This is not a symmetrical bond like the sigma orbitals were. It's not a symmetrical orbital, right? This looks kind of like those pi bonds that we saw in valence bond theory, right? It's not symmetrical. It's got two legs, kind of like the pi symbol does. So this is a pi molecular orbital formed from 2p orbitals. This is pi star, because this is anti-bonding. Higher in energy does not promote bonding. Then there's the third one in the z-axis. And so again, we can combine these so that the positive ends interact with each other and the negative ends interact with each other. And so now we get this bonding orbital. There's positive phase here, negative phase here. There is electron density shared that's pulling the nuclei together, right? If they interact destructively, then we get this big no man's land in the middle, and these guys get bent away from each other. So these are also pi, because kind of looks like a Greek letter pi, right? So this is pi 2p, and that's pi star 2p. Now, the relative ordering of those 2p molecular orbitals is not the same for all atoms. We're going to just look at boron, carbon, and nitrogen have a different order than oxygen, fluorine, and neon do. And I'll tell you how you can remember that these guys are different. The typical thing, which is the oxygen, fluorine, neon thing, is the sigma bonding is the lowest energy, and the sigma star bonding is the highest energy, and then the pi bonding and pi anti-bonding are in between. So if we draw that out, this is considered the expected order. So I have 3p orbitals here and 3p orbitals here. The ones on the x-axis can overlap end to end and form a sigma orbital and a sigma star orbital. And these are the two that are parallel to each other and overlapping side to side. And so pi orbital and pi star orbital. So this is the expected order. And then if we look at the s orbitals in that principal energy level, they're going to do what they did before. We're going to have one that's lower and one that's higher. Okay? Boron, carbon, and nitrogen. Be careful now. These are the ones that are different, and I'm not going to try to trick you with this. What's different here? Can you spot the difference between this part and that part? Yeah, these two switched order, right? Instead of the sigma one being the lowest, the pi bonding is the lowest, and then the sigma. The ones on the top stayed the same. So that's what's switching here. Like I said, I'm not going to try to trick you on this, but we're doing problems with it, and so it just is. Sorry. The reason is because there's increased mixing of the 2s and the 2px for those smaller atoms. Personally, I don't really care about the reason, and I'm pretty sure nobody else in this room cares about it. Okay, so what are we showing here? So this is the molecular orbital diagram without showing all of the atomic orbitals on the sides. Okay, so it's like we're just looking at this part, right? Just the part in the middle. And that's what we're showing in this table because it would take up way too much space otherwise. So B2, well, how many valence electrons does each boron have? It has 3, right? So we have 2 borons, so a total of 6 electrons, right? So those are going to go 1, 2, 3, 4, 5, 6. They're going to take their own orbital because they can, right? Carbon has 8 total electrons. 1, 2, 3, 4, 5, 6. Now they have to pair up. 7, 8. But this is the be careful now arrangement where the pi bonding orbitals are lower in energy than the sigma. And here's nitrogen. And if we calculate the bond orders for these, they go 1, 2, and 3. And if we look at the bond energy increases because higher bond order, stronger bond. Stronger bonds are shorter bonds, and so we see that the bond length decreases. After nitrogen, we get to the regular order where we have the sigma 2p being lower in energy than the pi 2p. So oxygen, 6 valence electrons each, so we've got 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then fluorine and neon. Now what we see is that the bond order is decreasing. The bond order for Ne2 is actually 0, which we did not expect Ne to make a molecule with another neon atom, right? But these bond orders are getting smaller, and so we see a decrease in the bond energy and an increase in the bond length. So this one has more anti-bonding electrons compared to the number of bonding electrons than, say, this one over here does. And that's what the bond order is doing. It's actually calculating that. So we're going to talk about magnetism again, paramagnetism and diamagnetism. So we know from experiment that oxygen is paramagnetic. Oh, I didn't know that. Well, let's watch this.
When liquid nitrogen is poured onto a magnet, the magnetic field does not affect the liquid. When we pour liquid oxygen onto a magnet, however, it is held by the magnet because oxygen molecules are paramagnetic. Paramagnetic substances have unpaired electrons.
Isn't that weird? Did you see that? Oh no, don't do that. it fast enough.
Those are paramagnetic.
See that? It looks like they're pouring water on a magnet, right? And the first one, you're like, oh, you're pouring water on these two metal things, and it goes straight through. Sure, of course it does. And then you do this one, and it's like it's sticking between the magnets. What? What's going on? So this is not water. This is nitrogen gas and oxygen gas cooled down so it's incredibly cold and it actually becomes a liquid. And so you can pour it like a liquid, and the oxygen sticks between the poles of the magnet. The nitrogen does not. This tells us that there's something different about how its electrons are arranged. The oxygen molecules are attracted to that magnetic field. The nitrogen molecules are not. So the paramagnetism is a direct result of unpaired electrons. So if we go back and look at nitrogen and oxygen, here's the molecular orbital diagram for oxygen. Oh wow, look there. Two unpaired electrons, right? So this is predicted to be paramagnetic, and as the video shows, it is. Nitrogen's over here. Nitrogen has all of its electrons paired up. It's diamagnetic. It's not attracted to a magnetic field. That's why it goes straight through the magnet. So this shows an important thing about molecular orbital theory. Molecular orbital theory explains the paramagnetic behavior of oxygen. Lewis theory and valence bond theory do not explain this. So if we look at the Lewis diagram for O2, do you see any unpaired electrons? No. You would predict that then this is diamagnetic and would not stick in the magnet. Here's an illustration of the valence bond diagram for oxygen. That double bond is from an overlap end to end here of these p orbitals, and then we've got the side to side of another pair of them. And so, do you see any unpaired electrons in this one? See, these are paired up in this bond. It's all paired up again, right? So the Lewis model and valence bond model do not explain this behavior. Molecular orbital theory does. Draw a molecular orbital energy diagram and determine the bond order for the N2 plus ion. Do you expect the bond to be stronger or weaker than the N2 molecule? Is this diamagnetic or paramagnetic? So let's just go back here. So this is N2, and it had a bond order of 3. And this is the be careful now part, where the pi 2p orbitals are lower in energy than the sigma, okay? And the good news is I'm not going to make you draw the molecular orbital diagrams. On the exam, they'll be given to you, and you either have to fill the electrons in or look at them and make evaluations. But you don't have to draw these, okay? But I have to draw them here because. So for nitrogen, we've got 2s. Do it better this time. So when those overlap, we get one that's lower in energy and one that's higher. So this is sigma star, 2s, and this is sigma, 2s. And then we have the p orbitals. 2p and 2p. And when these overlap, we get 1 sigma and 2 pi orbitals. And because this is nitrogen, oh Let's see what I did there. The sigma one is going to be higher in energy than the pi one. And then you got the pi one here and a sigma one up here. So this is pi 2p, that's sigma 2p. This is pi star 2p and sigma star 2p. Again, you won't have to draw that, I'll give it to you. So we're looking at N2 plus molecule, or ion. So we've got a nitrogen and a nitrogen ion. Again, we're just looking at valence electrons. How many valence electrons does a nitrogen atom have? What group is it in? Group 5, right? It has 5 valence electrons. So 1, 2, 3, 4, 5. Okay. This is N plus, meaning it lost an electron, so it only has 4 valence electrons. So 1, 2, 3, 4. The most important thing is knowing the total number of electrons. Because filling these parts in, these atomic orbitals, remember these are the molecular orbitals in the middle, and these are the atomic orbitals that they were made from. We really don't need to look at this part at all. We're interested in this part. And for that, we don't need to know which atom the electrons came from. We just need the total number of electrons. So 5 from this and 4 from that, that's a total of 9, right? So I'm going to fill this in using the same rules we used for other orbital diagrams. So 1, 2, 3, 4, 5, 6. It's going to take its own space because it can. 7, 8, 9. Okay? So this is saying find the bond order. Well, which of these are bonding orbitals? It's this one, and this one, these two, and this one, right? Those are the bonding orbitals. Where are the anti-bonding orbitals? Well, those are the ones with the stars, right? That would be these guys. Okay, so doing the bond order, we're going to count up all the electrons that are in the yellow ones, the ones without asterisks. So I have 2, 4, 6, I have a total of 7. 7 electrons that are in the bonding orbitals. And how many in anti-bonding orbitals? Just the 2 here, right? So 7 minus 2, that quantity divided by 2. So that's going to be 5 halves, or 2.5. So that's the first answer in this question. Determine the bond order. And the bond order is 2.5. Based on that, do we expect this bond to be stronger or weaker than in the N2 molecule? We looked at that one, and that one had a bond order of 3. So is this one stronger or weaker? It's weaker because its bond order is smaller. So it's weaker than N2. Is this diamagnetic or paramagnetic? We're looking at these electrons in the molecular orbitals. Are they all paired up? No, one of them is not. When they're all paired up 2 by 2 like Noah's Ark animals, that's diamagnetic. So here we have one that is not, and so this is paramagnetic. This will be attracted to a magnetic field. Yes.
So if you were working with something from like, period 3, instead of 2s, you would have 3s.
Right.
Kind of thing.
Mhm.
Okay.
Yep. The the core electrons, what's going on with the 1s electrons? Well, those are making their bonding and anti-bonding orbitals as well. But those are going to be the same for everything going forward, and contribution to bond order from that is 0, so we don't need to look at it. But that's happening underneath.
We're just worried about the valence.
We're just going to look at valence electrons, just like we've been doing for other things. So these are the sorts of questions that you could have on an exam. I would give you this diagram without the electrons filled in, and I'd say, maybe O2 plus. What's the bond order? Is it diamagnetic or paramagnetic? How do you do that? Well, you look at that ion or molecule, figure out how many valence electrons are there. O2 plus, right? It's missing 1. Each oxygen would have 6 normally. 6 and 6 is 12. We're missing 1, so it would be 11. And you would put your 11 electrons in here, and then calculate a bond order and look to see, do we have unpaired ones, or are they all paired up? Okay. So let's look at heteronuclear diatomic molecules. So now we still have 2 atoms, but these atoms are not the same element. They're different elements. This is the Mo diagram for no. So here we have nitrogen, its atomic orbitals, and here we have oxygen and its atomic orbitals. Oxygen's more electronegative, so its atomic orbitals are lower in energy. You're not expected to know that, I'm just telling you. These are lower in energy than those. So when these combine, right, they're not going to contribute equally to both of these. So this one contributes more to the bonding, and this one contributes more to the anti-bonding. And so, this is kind of staggered up a little bit, but we're ending up with the same thing in the middle. Okay? So no nitrogen monoxide, we've got 5 electrons from the nitrogen and 6 from the oxygen, right? So 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We can look at this unpaired electron and say this is a paramagnetic molecule. It would be attracted to a magnetic field, and we could calculate the bond order. Let's do that. So, just to help us, I'm going to highlight in red the anti-bonding orbitals and the bonding orbitals in yellow. Just makes it a little easier to look at. So the bonding orbitals, 2, 4, 6, 8, right? 8 electrons there. And then I'm subtracting the ones that are working against bonding. So this is anti-bonding. There's 2 there, and there's 1 up here. So that's -3. And so this is also going to be 5 halves, or 2.5. Okay? Here's hydrogen and fluorine. Fluorine is the most electronegative element, and so this one's really wonky. All of its atomic orbitals are lower in energy than hydrogen's 1 orbital. So when this combines, you get a little wonky, right? So here we have S interacting with P. Well, this S can overlap with the P orbital that's sticking out to it, but then it's done. And so what happens to the other 2 P orbitals? Well, they're just going to sit there and they're not going to do anything. They're not for bonding, they're not against bonding, they're non-bonding. use molecular orbital theory to predict the bond order of the FO minus ion. Yeah, to save time, I'm not going to do this one. But again, the way you would do this is you'd say, okay, well, fluorine has 7 valence electrons, oxygen has 6. 7 plus 6 is 13. The negative means it got an extra one. I've got 14 electrons. You take that orbital diagram. Let's use a regular one. And you put your 11 electrons in. So let's just co-opt this guy over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Paramagnetic or diamagnetic? Diamagnetic, they're all paired up. And then the bond order, again, you'd count the ones in the bonding orbitals, that's this one and this one and this one, and you just subtract the anti-bonding. Okay, so this is why we look at this. So we looked at the diamagnetic, paramagnetic behavior of oxygen, right? And we saw that molecular orbital theory explained this where the other theories didn't. Here's another place where molecular orbital theory explains something that Lewis and valence bond do not. If we look at ozone, we have looked at ozone. This would be the Lewis structure, and we've said there's resonance, right? That second bond there, that second pair of electrons, is actually not flipping back and forth. It's actually shared across all of that. But Lewis theory has no way to show that. In the valence bond model, here's that second bond. It also is localized between these two atoms, right? So we see a double bond and a single bond. That this bond is different in length and strength than that one. But we know experimentally that they are identical to each other. So this is how molecular orbital theory works. So now that problematic pair of electrons is in orbitals that are delocalized over the entire molecule, right? So we have one pair of electrons here that's spread across 3 atoms. And this gives us predictions that match up with experimental results, that these bonds are the same as each other. They are not different, they're the same. So molecular orbital theory explains that. This is a molecule called benzene, which you'll become familiar with if you take OChem. So it's got a 6-carbon ring, and in Lewis theory, there's 3 double bonds there, so there's resonance. So is this a double bond and that a single bond, or is this a single bond and that's a double bond? Actually, it's neither, it's in between, but the Lewis model can't handle it, and so this is the best we can do. This is valence bond theory. So this pair of electrons and that pair and this pair that are being problematic because we can't say exactly where they are, they're actually distributed across the whole molecule. And so this gives us predictions that are consistent with experiment, that these bonds between all these carbons are identical to each other. They're not alternating differently. They're all the same. So this slide here really is the whole reason we need to talk about molecular orbital theory at all, is so that we can understand going forward that we can have electrons that are shared over the entire molecule and not just between 2 atoms in a nice little Lewis bond that we can draw. Any questions?